Tout d'abord, je voudrais remercier les organisateurs pour l'invitation. Je suis très honoré. Deuxièmement, secondly, let me say that everything I'm going to do today is joint work with Łukasz Koszyński. He's sitting back there, so address all complaints to him. And this is a conference on interpolation, as we learned. First, let me explain why I'm going to talk about extension theorems. Sorry about that. Maybe put it in my pocket. So an extension theorem and an interpolation theorem, I claim, are really the same thing from a slightly different perspective. So in both setups, I have some set V sitting inside some larger set omega. And I'm given a function f on V into some codomain y. And then you want to find some function phi from omega to y that has the same values as f and is in some appropriate class. Now, the difference between interpolation problems and extension problems is one of perspective. So in an interpolation problem, frequently the set V is finite or discrete, doesn't have much structure. When it's finite, the existence of some extension is often automatic. But what you're interested in is some sort of optimal extension, the one with the smallest norm or best properties. In an extension problem, V is normally a fatter set that has some structure, and then you want to know whether then F preserves this structure. You want to know whether you can find a function phi on the big set that also has the structure. So there's many, many examples of extension theorems. Let me just give a couple that everyone's heard of. For instance, there's the Hahn-Banach extension theorem. If you haven't heard of the Hahn-Banach extension theorem, you're in the wrong room. There's, let's see, the Tichy extension theorem. There's Hartog's extension theorem. Now, these are all examples of always theorems. Each of these theorems says that for an appropriate setup, you always find an extension. Now, there may be some work improving it, but there's a sort of opposite extreme. So to give an example of sort of the opposite extreme of the extension theorem, let me give you a theorem of Neven-Linna's. So you start with some function f defined on an interval. Let's say the interval -1, 1. So we have a function on an interval here. And then the question is, can I extend this function? So I think of this as being in the complex plane. Can I extend the function to the upper half plane so that it's holomorphic and maps the upper half plane to itself? So the question is, does there exist phi from the upper half plane to the upper half plane that extends f in the obvious sense that if I take vertical limits, I recover f? So then by reflection, it really extends to the lower half plane as well, everywhere except this slit. So what was Neven-Linna's answer to this? Well, let's start with a single function. Suppose I take the function x over 1 minus tx, where, so this is a function of x, and t is some number between -1 and 1. Well, this has a fairly obvious guess for what the extension might be. If I look at z over 1 minus tz, this is certainly a holomorphic function in the upper half plane. And if I calculate the imaginary part of this, well, I can multiply above and below by complex conjugates, and what do I get up here? I get z minus t z squared. So the imaginary part of this is real, this is positive, so the imaginary part of this is the same as the imaginary part of z is positive if the imaginary part of z is positive. The upper half plane, this is the set where the imaginary part is positive. So here I have a candidate function that has an obvious extension. And if I take any convex combination of these functions, they're still going to be holomorphic, and since the upper half plane is convex, it's still going to map into the upper half plane. So if I take some integral from -1 to 1 with respect to some positive measure, this will have an extension to the upper half plane. I just make the brilliant substitution. I replace x by z. And that's Neven-Linna's answer. F has to be, so you get such a thing if and only if f has the form this plus some constant. Now the difference between Neven-Linna's theorem and these theorems is kind of the opposite extreme. It says you only have an extension if you can write the function in such a way that you obviously have an extension. So in real algebraic geometry, they call this having a certificate. So a certificate means you're writing an expression in such a way that it obviously has some property you want. For example, you prove that something is non-negative by writing it as a sum of squares. That's a certificate. The Neven-Linna's theorem says that you can extend, you can solve this problem if and only if you have a certificate that shows you can solve it. Oops, I'm probably breaking the electronics here. Okay, you go up there, and now I've never been in a lecture hall before in which all of these work. There's no. So, oops, that was a little too high for my short arms. So, what's the situation Łukasz and I have been looking at? So, our case. Omega is going to be some domain in several variables. So let's assume it's bounded, connected, open. V, living inside omega, this will be, well, we'll think of it as some nice subvariety. We'll be a little bit more specific later, but we're thinking of this as some nice subvariety. So here we have a picture, here's omega, and then V is some set sitting inside it. And then we're going to be looking at functions f, which are holomorphic, and critically, they take their values in the unit disk. And then the question is, let's make this a dotted line. Oh, let me be high tech, I'll make it a colored line. Do you have an extension to the whole domain, which is also takes values in the disk? Well, let's look at a couple of examples. So suppose I take omega to be the ball in two variables. And I take V to be the union of D cross 0 union 0 cross D. So if I look at the real projection of this, I take this cross. And I define F to be Z1 plus Z2. Well, clearly on the cross, one of these two terms is 0 and the other one is in the unit disk, so this will take values in the unit disk. But if I had such an extension, so suppose I have some phi which extends it, I know enough about phi at 0 to calculate its derivative. I have two pieces of information. So I can tell you that d phi at the origin has to be the vector 1, 1. And now I look at the, sitting inside the disk here, as inside the ball, I have a diagonal disk. So this would be the set of zeta, zeta. And if you apply Schwarz's lemma on this disk, and you have that the derivative in this direction is too large. So you're going to so Schwarz's lemma tells you that the function restricted to this disk has to take 0 to 0. This derivative is too big. You rescale. So normally Schwarz's lemma, you learn it on the unit disk, but you just rescale and you find that this is root 2 too large to possibly work. The length of this is root 2. It can be at most 1. So it violates Schwarz's lemma on this embedded green disk. So this set doesn't have the extension property. And in some sense, the reason it doesn't have the extension property is because we had a cross. The holomorphic functions can see something in this direction, which is hidden from the set V. So on the set V, you're only allowed calculate norms here and here, but because of the rigidity of holomorphic functions, when I know the derivative in this direction here, I get something. Notice this function we've chosen is going to be very big in this direction. So I can wiggle it some. There are obviously other possible extensions than this one, but however I wiggle it, I'm always going to violate this derivative property here. So the takeaway from this is that sets that have the extension property, oh yeah, so let's give this a name. So let's say that V has the extension property, and you can always do this. If phi always exists. Sets that have the extension property can't have crosses or cusps or bad singularities or singularities like that. So for a second example, again I'm going to work in the ball. And now I'm going to let V just be the set of points Z2 squared is equal to Z1. Intersect the ball. So it'll be some sort of curve like that. Now, if I project this onto, so V is really a graph. It's the set of, if I parameterize with Z, it's a graph over some disk down here, but the radius of this disk Well, so you solve the equation for what you get in the projection, and you get that z is less than or equal to some number which is about 0.78 something something something. It's the square root of root 5 minus 1, the square root of 5 minus 1 over 2, if you want to be precise. But the point is it's less than 1, which is kind of obvious even without doing any calculations. So now if I take f of z1, z2 to be, so say 1 over 0.79 times z1, this number is bigger than this number, therefore on this parabola my function f has modulus less than 1, but again by Schwarz's lemma, just calculating the derivative at 0, my derivative at 0 is larger than 1 problem. So this was bad because of singularities. This is as smooth as you could imagine, but the reason it's bad is that in some sense V is too curved. In some sense V is curved, in a sense that we'll make precise in a little bit. Oops. You go all the way up there. And then you go up to there. Third time's a charm. But neither of these examples are in any way pathological. So, as all good analysts, you step back and say WWND, which obviously stands for what would Nev and Lina do? Well, we want to look for something that guarantees you would have an extension. So when can you guarantee you have an extension? It looks like that even in relatively benign cases you don't. So in what cases do you have an extension? Well, sticking with the disk, suppose we just take the equatorial plane of the ball. So sitting inside B2, I have D cross 0. And from this equatorial plane, you have what Xiaojun Huang calls the idiot's extension. So if I'm given f on the equatorial plane, I define phi on the whole ball to just forget about the second coordinate. And this obviously works. It has the same range. And if you think about it for a little, you see what makes this tick is that the projection from the ball onto the equatorial plane is a retract. So, what's a retract? A retract, R, is a holomorphic function that maps omega to V, and critically, if I compose it with itself, I get the same thing. So it's the identity on V. R restricted to V is the identity restricted to V, equivalently. So if I have a retract, then I always have an extension. So if R is a retract, then the formula phi of Z is F composed with R of Z automatically gives me an extension of any function F defined on V, because this is holomorphic, and the range of the right-hand side is exactly the range of f, so it has to lie inside the unit disk. So we now may be led to guess that perhaps, since it's hard to get extensions, maybe you need a retract. So here's the goal theorem. Goal theorem. If V, and then maybe we have to put some subhypotheses, then V has the extension property if and only if V is a retract. Well, we're going to need to put some restrictions on V, because if I take even a nice set here, and now I start throwing points away until I'm just left with some dense subset peppered with holes, well, the holomorphic functions on this dense set are going to be exactly the same as on the original one. So whereas a retract is a very rigid geometric object. So we're going to have to at least assume that V is geometrically nice in some way. So let's be generous to ourselves and say if V is relatively polynomially convex, which means V closure is polynomially convex, and V closure intersect omega is V. So this means it doesn't have any holes. If I just removed a point here, I take the punctured disk, that would violate this second condition. So now V is a relatively nice object sitting inside omega, and now we can ask whether having the extension property forces it to be a retract. And let me emphasize, by the way, that the fact that the range of this holomorphic function is D is critical. If I just wanted to extend every holomorphic function from V to a holomorphic function on omega, then Cartan's theorem B says you can always do that if V is an analytic subvariety. So what makes this so much more rigid is the insistence that maps into the disk can be extended to maps into the disk, not into the whole plane. The boundedness is critical here.
Define what you mean by a map to be a retract, but not what you mean by a set to be a retract.
Oh, a set is a retract if it's the image of R. I.e. V equals R of omega, some retract. Thanks, Jan Frederick. Okay, are the sideboards visible? So the theorem, oops, I'm running out of time. So the theorem I want to talk about is that if omega is strictly convex, that means every boundary point there's a plane that touches that point and no other point, and two-dimensional, then the goal theorem is true. And so I'd like to try and explain why both convexity and two-dimensionality play a role. Before I do that, let me just give a little bit of history here. So the first theorem I know of this nature was one I proved a long time ago with Jim Agler, which says that if omega is D2, then the goal theorem holds. But the critical importance of convexity was shown in a recent paper of Agler, Lykova, and Young. I think it came out last year. And they showed that for the symmetrized bidisk, which is not convex, the goal theorem fails. There are sets with the extension property that are not retracts. And this is badly not convex. So I want to show, so this is, you can weaken this hypothesis, but I want to show how convexity helps and why two-dimensionality matters. Oops. So first we need a little bit of complex geometry. A Kobayashi extremal for a pair lambda mu and omega. So here's omega, here are 2 points, here's omega, and here are 2 points lambda and mu. A Kobayashi extremal is a map from the unit disk into omega, so the pre-images of lambda and mu are as close together as possible. It's the infimum over all such maps. Here's a map K from D to omega, so it has to hit lambda and mu, so say K of Z is lambda, K of W is mu, such that the distance, the pseudo-hyperbolic distance between Z and W is as small as it can be. And then the image of a Kobayashi extremal is called a geodesic, range of K is called a geodesic. And then there's a very important theorem of Lempert from the 80s, which says two things. If omega is a bounded and convex domain, the first property is that every geodesic is a retract. Which he expressed as saying every Kobayashi extremal has a left inverse. And every pair of points has a geodesic connecting them. So it's not obvious that you can minimize this map, but Lempert proved you can. Okay. Need to speed up a little. So, to prove this theorem, there's sort of two pieces to it, in both of which convexity plays a role. So first, if we drop the two-dimensionality, we just have, if omega is strictly convex, phi has the extension property and is relatively polynomially convex, then V is a union of geodesics. Given any two, if you take any 2 points in V, the whole geodesic containing them has to be in V. And V is a union of geodesics. It's called geodesically complete. And the argument for the proof of this kind of goes as follows. Morally, up to a change of variables, so if I take 2 points in V, the geodesic through them I can think of as a sort of slice through the fat part of the set omega. And your retract is just going to be projection down. So the function f I'm going to exploit will be the function that basically takes the equatorial plane onto the disk. If V was not totally geodesic, it would be missing, so V would be some subset that has these 2 points, but it doesn't have the entire geodesic through them. Instead, V is maybe it's other stuff as well, but V would live here. So the projection of V would not hit the whole unit disk, it would miss a little part of it. So this is an idea that's originally due to Pascal Thomas. So if I have some function from V onto the disk that misses a tiny part, I now compose with the Riemann map from this bitten off piece of the disk into the whole disk. And that will stretch. So these 2 points that get mapped to here get mapped further apart in this stretch. So now I take f to be this composition. I've taken these 2 points and I map them a long way apart. Well, if I have some extension of f to a function phi on all of omega, it's taken these 2 points and it's mapped them further apart than they're allowed to by the geometry of the set. So this will give us a contradiction. Again, just as in these 2 elementary examples here, we're basically violating Schwarz's lemma. Seems to be the only game in town. Okay, so you kind of use convexity or some variant on convexity to get this. Where does 2 dimensions come in? Well, that's in how you finish off the argument. You start. So here's omega. If V is just a single point, then I'm done. There's nothing to do. If V has 2 points, then since it's totally geodesic, it has to contain the geodesic through it. By Lempert's theorem, this is a retract. So if this is all of V, again, we're done. If it's not, V contains this green line plus another point here. Now I use the second part of Lempert's theorem. And so let me point out, by the way, for the symmetrized bidisk, it is true that every geodesic is a retract. It's not true that every pair of points has a geodesic connecting them. So even though it's not convex, the first part of the theorem is true. The fancy way of saying that is the Kobayashi and the Carathédori metrics are the same. So I take this point here. This is in V, and all these points are in V. Therefore, every geodesic from here to here has to lie in V. So I start filling these out. I draw these geodesics. And I get, eventually, I get a set with interior just by looking at the geodesics through this extra point as I range across V. Once I have a set with interior, and this is where the fact that I'm in 2 dimensions kicks in. Once I have a set with interior, then I'm done. Because if I take any other point that might be in the set, so suppose I had some point out, suppose I take some point out there, which I'm trying to prove that in the 2-dimensional case, V is all of omega. If I take any other point here, I just draw whatever geodesic I get between there into the interior of this set. There are 2 points here that are definitely in V, therefore the whole geodesic through them is in V, therefore this original blue point was in V. So we only have three possibilities. We either have a single point, we have a one-dimensional retract, or we have the whole set. Okay, so what happens when you want to go beyond 2 dimensions? Well, the totally geodesic property persists. The problem is that retracts are not understood if the dimension of the set is more than 1. So there are a couple of special cases where you can just work it out. So for the ball, it's fairly easy to work out the retracts, and the goal theorem is true for the ball in any number of dimensions. For the polydisk, retracts are, again, the obvious things. They're just graphs of functions, but for all other domains, really nothing is known about retracts. So let me just end with what I consider a significant open question. When are totally geodesic sets retracts? This seems to be very challenging when the dimension of the set is more than 1. Thanks, I'll stop here.